Okay, so we're ready to go for chapter section 18.2, and this is still the chapter on chemical equilibrium. Today, what we're going to be looking at is what's named LeChatelier's principle. And let me go ahead and get my pointer started here. So up here is the name LeChatelier's principle, named after a French guy named LeChatelier, obviously, but I don't remember his first name or anything else other than the fact that he came up with this principle. Has to do with chemical equilibrium. So what we're going to do today, today's PowerPoint presentation's not going to be as long as the last one. Basically, what we're going to do is I'm going to give you the principle is, then we're going to see it in action. Okay, so first bullet point on this first slide gives you what LeChatelier's principle is. So LeChatelier's principle, as stated, is the following. When a stress is placed on a system at equilibrium, the system shifts in a direction to counter that stress. That is LeChatelier's principle. All right, so when somebody asks you, hey, what's LeChatelier's principle? You say, well, when a stress is placed on a system at equilibrium, the system shifts in a direction to counter that stress. And there you go, you would be correct. The bigger question is, what the heck does that mean and how would I ever use that? Okay, so that's what this video is basically about. It's like, let's interpret what LeChatelier's principle is. And basically, to get an understanding of what LeChatelier's principle is and when it's put to use, we have to see what the conditions are that we'd use it. So basically what LeChatelier's principle does is it allows us to understand what happens when we have a system at equilibrium. So a system is nice at equilibrium. And if you recall from the last video, a system is at equilibrium when there's a certain amount of reactants and products. There's reactants and products both in there, and they have a certain proportion of reactants to products that equals to the equilibrium constant. Right? So the amount of products divided by the amount of reactants, and there's all that whole equilibrium expression / law of mass action equation that we need to use for that. But basically, just to summarize it, the ratio of products to reactants is a certain ratio, which we call the equilibrium constant. In the first section, we learned how to get to that. We learned how we define chemical equilibrium and how the equilibrium constant defines the chemical equilibrium and how that equilibrium constant is products over reactant ratios, basically. We have to take into account the coefficients. They become exponents in our equation. We went over all that in the last equation. So section 1 told us how to define equilibrium and how to get to equilibrium. And we really did learn how to get to equilibrium. Unfortunately, we're not going to have time for that. There's actually some problems where you can actually kind of figure out what would be the concentrations at equilibrium. But once again, I think we've run out of time in the school year, so we're not going to be able to get to that. But 18.1 talks about how to establish chemical equilibrium. This section, 18.2, talks about what happens when you have equilibrium and then you go and mess it up, right? Everything was nice, everyone was happy, there was equilibrium, and then suddenly someone comes in and messes it up. How does the chemical reaction behave? And it's the chemical reaction, or you can call it the chemical system, that is the one that basically fixes itself. So in order to understand LeChatelier's principle, we have to understand that there are 3 ways you can mess up equilibrium. We call them the 3 stresses. So down here in the second bullet point, we talk about the 3 stresses. What are those 3 stresses? And by the way, these stresses are not the same stresses like you guys have or we have. They're not psychological stresses. They're not, oh, I've got a, final exam coming up. Oh, here comes that girl that I want to talk to, but I don't know what to say. Or, oh, here comes this person and I don't want to see them. They're not that type of stress. These are stresses that we put on a system that are physical property type stresses. So let's take a look at them. The first one is concentration change. Everyone is at equilibrium, everyone's happy, then suddenly you mess up the concentration, you change the concentration of one of the participants in your chemical equation or chemical equilibrium. So that's one of the stress. This is concentration change. The second stress is temperature change. Right? You've got a system that's nice at equilibrium, and every chemical system has an equilibrium constant, but that constant is only good at a certain temperature. So as you change the temperature, you also change the equilibrium constant. And so, what happens when you change the temperature, and how does that affect the equilibrium? And the last one is when there's a pressure change. You change the pressure of your system. And as you can see here in parentheses, I put it secondary to volume change. So you have a pressure, and that pressure is related to a certain concentration. And then when you change the volume, it changes the total pressure. What happens to the system? Okay. Now, here's some good news for some of you guys. Not all of you, but some of you. There's very little math today. It's more rational, logical thought that's going to be necessary in order to do our problems today. Right? So let's go on and see how we're going to do this. So let's talk about the three stresses, how they affect equilibrium, how the system is going to fix itself after somebody else, us or somebody else, has messed up its equilibrium position. All right, so the first stress we said was a concentration change. So let's go ahead and take a look at this equation I have right here. I have 2NH3 plus 3O2 goes to form 2CH4. I'm sorry, plus 2CH4. They're all three of those are reactants. Goes to form 2HCN plus 6H2O. So the question is, how does a concentration change affect this equation? Once again, we're starting with equilibrium. So these are all at equilibrium. So the concentration of NH3 and O2 and CH4 and HCN and H2O are such that you are at equilibrium. Right? And when you take the concentration of HCN squared divided by the concentration of H2O to the sixth, divided all that by NH3 concentration squared times O2 concentration cubed times CH4 concentration squared. When you plug those numbers in, you get a number, an equilibrium constant. And these concentrations match that equilibrium constant when you plug the numbers in. Right? So what are some of the stresses you could have? Here are a couple of stresses. First off, let me explain what I have here. I have a little table, and this table has three columns. There's a column for stress, and the stress is what somebody did to this system. We start off at equilibrium. Everyone was happy in their proportions to everybody else. And then we put a stress in it. We messed up. Here, as you can see, we increased ammonia, or we decreased it, or we increased HCN, or we decreased HCN. So those are the stresses. We just added more of one substance or took away more of a substance. So that's your stress column. The counter to that stress is just the opposite of the stress. The stress is what was done to the system. The counter is the opposite of the stress. This is what the system is doing to fix it. So it's been pushed to one side, and so the reaction wants to kind of push back in the other direction. And what it's going to do is it's going to shift in one direction or the other. It'll shift either to the right or to the left. And this is where a lot of students have been having a hard time trying to figure out, what that means. When a reaction goes to the right, we say that then our reactants are going to turn into products. So the concentration of HCN here will increase, the concentration of H2O will increase, and the concentration of all your reactants will decrease also. NH3, O2, and CH4. Okay. And of course, this is specific to this chemical equation because these are the chemicals involved in this chemical equation. If there was another chemical equation, it'd be different chemicals, but the idea of a reaction going to the right is the same. If the reaction goes to the right, which it means that it turns reactants to products. So concentrations of NH3, O2, and CH4 go down, and HCN and H2O go up. Okay. So that's what it means by when a reaction goes into a certain direction. And before we can go ahead and figure out what's going to happen to any individual substance, we need to figure out what direction the reaction will go. So I can ask a question like, what happens to the concentration of HCN if we increase the concentration of NH3? That's the way that a question might be asked to you in your homework. So what is the effect on HCN when we increase the amount of NH3? Okay, so if you look at, this is one of the examples that I have here. So our stress is increase in NH3. So in order to figure out what's going to happen with HCN, what I want to do is figure out which direction the reaction is going to go to. If it goes to the right, then it'll increase. If it goes to the left, that means that, I guess I didn't show that. When the reaction goes to the left, then all the things on the right turn to stuff on the left. So we will decrease the amount of HCN, we will decrease the amount of H2O, and we will increase CH4, O2, and NH3. Okay. So, that's what we're kind of looking for when we do these problems. Okay, so once again, there's an increase in NH3, so the reaction wants to do the opposite. Okay, think as the reaction is some rebellious thing, or once again, you get pushed to one side, you want to push back, right? So that's what it does. So if we increase the amount of NH3, the reaction is going to want to do the opposite. It's going to want to decrease. And so the question is, in which direction will NH3 decrease? Right? We increased it, so the reaction itself wants to decrease it. Well, when you want to decrease a substance, the amount of a substance, then what you do is go away in the direction away from it. Right? That way, it will be kind of a reactant, whether it's going right or left. If it's going away, you're going to turn your NH3 into something else. And in order for NH3 to decrease, we need to make the reaction go to the right. And that's why we have this right here. The direction goes to the right. And that means that when the reaction goes to the right, O2 will decrease, CH4 decrease. If they had asked you what's going to happen to the concentration of CH4 as you increase NH3, you'd say also it's going to decrease. And since the left side, the substances on the left side are decreasing, the substances on the right side are increasing, right? In other words, NH3, O2, and CH4 are turning into more HCN and H2O. So originally I asked the question, what happens to the concentration of HCN when we increase the amount of ammonia? Well, because we increased the amount of ammonia, the reaction wants to decrease it back. In order to decrease it back, the reaction is going to have to go away from it or to the right. So once the reaction is going to go to the right, we can see that HCN is on the opposite side. And so if it's going to the right, it's going toward HCN, so we get an increase in HCN. Okay, so if the question asks you in what direction does it go, you just say it go to the right. If the question asks you how does it affect the concentration of HCN, you say it increases. How does it affect the concentration of H2O? Well, it increases. Or how does it affect the concentration of CH4? Well, it decreases. Okay. And that's basically what you're going to be doing for the problems for this one. Okay, you're going to be trying to figure out, do they increase, do they decrease? It's very qualitative. It's not quantitative. You don't have to actually calculate numbers out. You just have to kind of know which direction the reaction is going. All right, so the second problem, and that's just kind of the opposite. So the first one, we increased the amount of ammonia. The second one, we decreased the amount of ammonia. So once again, when you decrease the amount of ammonia, the reaction wants to do the opposite, and that means it's going to want to increase it back up again. Once again, it's a rebellious reaction, doing the opposite. In order to increase the amount of ammonia is over here, we have to go toward, to get more, you have to go toward ammonia. So in order to go toward ammonia, we have to go to the left. And that's where we get this. Okay. And so in this case, what happens to HCN? Well, if this reaction is going to the left, the concentration of HCN drops. So does the concentration of water. These guys all drop. Now this is supposed to be an arrow. And the concentration of all these guys increases. Now for ammonia, it probably decreases overall because we actually decreased it by a chunk, and then the reaction increased it back, but probably not enough. You know, they won't be asking you what the concentration of the thing we're changing, what's going to happen to it. If you're dropping it, it drops overall. I mean, you may get a little bit of it back, but probably not enough to compensate for what has been already lost. Okay. So we just saw what happens when you have an increase in a reactant and a decrease in a reactant. Okay. So let's go ahead and clean this up again. Now, I did a couple more because we can also do the same thing with products. What happens when you change the concentration of a product? Here, HCN is a product. And so what happens when your stress is not changing a reactant, or it's changing a product? By the way, for these first two, I just did ammonia. I could have done O2 or I could have done CH4. Would have get the same answer because they're all reactants. So if you increase the amount of O2, the reaction is going to want to decrease the amount of O2. In order to decrease the amount of O2, it's got to go to the right. So it'll go in the same direction as over here. Okay. Now, if you increase the amount of HCN, that's a product. So you're going to increase the amount of HCN. So once again, the reaction is going to want to decrease it back down again. In order to decrease it back down again, you got to go, here's HCN, you got to go away from it. HCN's on the right. So let's go away from the right, which means toward the left. Okay. And that's why we get this answer right here. Now, if they'd ask you what happens to the concentration of CH4 when you increase the amount of HCN, well, you increase the amount of CH4 because once the arrows go on the left, that means that everything on the left is increasing and everything on the right is decreasing. H2O would decrease. Okay. Now, what happens as I erase over here? When you decrease the amount of HCN, once again, once you get the stress, you decrease the amount of HCN, the reaction wants to counter that stress. And so it increases the amount of HCN. This is the opposite. How do you increase the amount of HCN? You got to go outside toward HCN. Once again, HCN is right here. We got to go to the side toward it. So therefore, our arrow points to the right, which means that we're going to increase the amount of H2O and decrease all three of these guys over here. Okay. And so this table basically shows you just about everything that can happen when there's a concentration change. What happens when you increase a reactant or decrease the concentration of a reactant, or increase the concentration of a product or decrease the concentration of a product. Either way, you can figure it out. Okay. And by the way, let me just go ahead and go back here real quick because, you know, I have this counter to the stress. Remember that LeChatelier's principle says when a stress is placed on a system at equilibrium, the system shifts in a direction to counter that stress, right? So there's the counter of that stress. That's what the reaction is wanting to do. Okay, so I just want to point that counter is just part of LeChatelier's principle. All right, so that's concentration change. That's our first stress. Hopefully that's kind of understandable, right? Once again, it's just a lot of logic. It's a lot of stepwise logic. You got to do the stress, then figure out what the opposite is of that stress. Then you got to figure out which direction the reaction would go to produce the counter. So the reactor wants to produce the counter. Let's do the second one, and the second one's going to take 2 slides because there are 2 situations. All right, so what happens when there's a temperature change? Well, what happens when there's a temperature change really depends on whether a reaction is exothermic or endothermic. Here we're going to do exothermic first. You'll recall from chapter 16 that when a chemical reaction is exothermic, it's kind of like having heat as a product. So heat is going to count as a product. And once you know that heat is, a product, then you could just treat it like a concentration change. Just think about, do you want to increase the concentration of heat or decrease the concentration of heat? Okay? And once you do that, it becomes pretty easy. So let's take a look at this. If you increase the temperature, the reaction is going to want to do it? Decrease the temperature, right? Bring it back down. And in order to decrease the temperature, you're going to want to decrease the amount of heat. I'll just put it as Q because we learned that the other day, right? So we want to decrease the heat. Decrease Q, decrease heat. So how do we get less heat? Do we go to the right? We go to the left. Remember, when we want less of something, we move away from it. So since heat is on the right side, if you want to decrease the heat, the reaction goes to the left. And that's how we get this. So you could have the question, the question could ask, what happens to the concentration of HCN? HCN's right here. What happens to the concentration of HCN when you increase the temperature on this? Well, if the reaction is going to the left because of all this, that means that the concentration of HCN is going to drop. And so we'll have decreasing. And, a lot of times you would write it as, I have my little mouse here, so I don't know how well I write on this, but decreasing. All right. There we go. That's enough of me trying to write with a mouse today. I prefer, that's why I do the arrows. It takes less time. Okay. So yeah, that's how that worked. Let me erase all this. Now, if you cool the reaction down, in other words, you drop the temperature on the reaction, that's your stress. Once again, this is what we did to it. The reaction wants to do the opposite, bring it back up. So it wants to increase the amount of heat. So we're going to go toward the heat. And the heat's on the right, so therefore the reaction is going to go to the right. So in this case, the amount of HCN would drop. If you want more HCN for this reaction and it's exothermic, you better cool it down, because by cooling it down, it makes the reaction go to HCN. If you don't want there to be too much HCN, then what you do is you heat it up. Maybe it is a poisonous gas. So let's say you have this chemical reaction that's out of control. You're like, how do we keep it from creating too much hydrogen cyanide gas? Well, turns out you warm it up, because by warming it up, it makes the reaction go to the left. Okay. Now that's if all this is exothermic. Turns out that if the reaction is endothermic, all the answers are just switched back and forth. And that's the next slide. So let me go ahead and get to that. Erasing here. So let's use another reaction. 2NO plus O2 goes to form 2NO2. This one is endothermic. And so when something's endothermic, heat acts like a reactant. It acts like it's on the left side, right? If it was exothermic, it would be over here on the right side. But when it's endothermic, it's on the left. Let me get rid of that little X just so it doesn't get confusing here. Okay. Back to mine. Okay. So same logic. Temperature increases. So therefore, the reaction wants to decrease the temperature, which means it wants less heat. So when it wants less heat, it's going to go away from the heat. So therefore, it's going to go to the right because heat's on the left. Right? Here's the arrow. Sorry about my arrows. Sometimes they don't have good equilibrium arrows on Microsoft products, so I have to kind of use whatever I can find. So the reaction goes to the right because it goes away from the heat. Right? We want to cool it down. When you cool down this reaction, the reaction wants to increase the temperature back up, so it wants more heat. In that case, when it wants more heat, the reaction is going to go toward the heat, and it's go toward the left. All right, so we got to erase the first one, but that's all right. Okay. So in the first case, when you increase the temperature, you're going to get more NO2 product. Here, NO2 is right here. At lower temperatures, you're going to get less NO2 product and more NO product over here. Okay. That's how you do those. So once again, let me just go ahead and show you. If you look at these two slides, let me go ahead and get rid of all this stuff here. These two right here change. All right, everything else looks the same. So increase in temperature, reaction goes to the left. Decrease in temperature, reaction goes to the right. For this other one, increase in temperature, reaction goes to the right. Decrease in temperature goes to the left. The third stress. So those were the first two stresses. Concentration change was the first stress. Temperature change was the second stress, and you got to know if it's exothermic or endothermic in order to be able to answer the question for a temperature change. The third one is pressure change. What happens with the pressure change? And remember that this pressure change is secondary to volume change. So you'll recall that P times V, according to Boyle's law, is some constant, which means that pressure and volume go inversely from each other. So when you increase the volume, you're going to decrease the pressure. All right. In other words, if you expand a gas or set of gases, as we would see in a system, not just one gas, but a set of gases, if you expand a gas, then the pressure will drop. If you compress a gas, in other words, you drop the volume, then the pressure will go back up. Right? And so these are the type of pressure changes we're looking at here. We're not adding any we're not increasing pressure by adding any specific substance, in the involved in the chemical equation. The pressure of the overall system goes up. Okay? And in order to understand how this one works, I have to go back to this one first. In order to, I think I got these out of order, but that's okay. In order to understand how this whole thing works, you have to basically count gas molecules. You'll notice in this chemical reaction, all we have is gas molecules. In this chemical reaction, the reactant side, right, the side of the equation, has 7 gas molecules to it. 2 plus 3 plus 2. Add these numbers up, and you get 7 gas molecules. That's per mole of reaction, right? 7 moles of gas per mole of reaction. Or if you want to go with molecules, you can. And the products side has 8 gas molecules. There's 2 HCNs, and there's 6 H2Os for a total of 8 gas molecules. What this tells you is that when the reaction goes to the right, pressure actually increases. And the reason why pressure increases when the reaction goes to the right is because for every 7 gas molecules that are reacting, we get 8 gas molecules. You're actually getting more gas molecules. And if you'll recall the ideal gas law, as the moles of gas increase, so does the pressure. Right? So if N goes up, so does P. So if we want a reaction to go up, we would need to increase the number of moles of gas overall. It doesn't care about which gases they are. It's the total number of moles of gas, right? Because this is the total pressure. So if you have more moles of gas, you have higher pressure. If you have less moles of gas, you have lower pressure. So when the reaction goes to the left, the pressure actually decreases. And the reason it does so is because every 8 gas molecules are turning into 7 gas molecules. So you're actually losing a gas molecule every time this reaction kind of takes a turn. Right? 2 HCNs and 6 water molecules react. They turn into 2 NH3s, 3 O2s, and 2 CH4 molecules. That's a total of 7. We went from 8 gas molecules to 7. Therefore, we are losing moles of gas, and therefore we are losing pressure. Okay. So let's take a look at how this all goes. So if you increase the volume on a system at equilibrium, a bunch of gases in it, you're going to decrease the pressure. Once again, it was said earlier, volume and pressure are inversely proportional. So I could tell you the stress is, well, we expanded it. We made the volume bigger, put it into a bigger container. What that translates to is lower pressure. And just like before, if lower pressure is the stress, the reaction wants to counter that stress by increasing the pressure. And in order to increase the pressure, the reaction has to go in the direction of more gas molecules. So in this case, it's going to go from 7 to 8. It's going to go to the right, because by going in that direction, you're going to increase your moles, and therefore you're going to increase the pressure. That's why the reaction goes to the right. So by expanding or increasing the volume of the system, we're going to produce more HCN or more H2O. And we're going to get less CH4 and O2 and NH3. Okay? That's how you have to think about it. Once again, let me do that before I go back to that. Increase the volume means decrease in pressure, right? Because these are opposites. If the decrease in pressure is your stress, that means the reaction wants to do the opposite, increase the pressure. In order to increase the pressure, you got to go to the side with more gas molecules. And if, in this case, more gas molecules on the right, this reaction goes to the right. Sometimes there'll be more gas molecules on the left. In that case, you'll go to the left. Right? So you just go to the side with more gas molecules. The direction to the right here, in this case, is to the right, because that's the nature of this reaction. Okay. Let me go ahead and erase all of it. Now, if you decrease the pressure, in other words, you compress the gases, just jam them together, you're increasing the pressure. And so the reaction feels an increase in pressure. The reaction wants to do the opposite. It wants to decrease the pressure. Once again, remember, this counter here is always the opposite of the stress. So in order to drop the pressure, we have to go to the side with less gas molecules. In this case, less gas molecules is on the left-hand side. So that's why we say that the reaction goes to the left. And we make more of any of these guys on the left. Oops. And then less of any of these guys on the right. Okay. And so that is basically LeChatelier's principle in a nutshell. So on the homework, you're going to basically have to kind of think of it this way. There's not many numbers to use. It's just all a matter of what's the stress, what is the opposite of stress, that's the counter, and in which direction does this reaction have to go in order to achieve that counter to the stress. And it's always going to be either to the right, making more products, or to the left, making more reactants. Okay, and then from there you can pick out which one they talk about. Okay, so hopefully that was helpful. That was the whole thing this time. And so until next time, stay safe and have a good day.